And welcome to this fourth and almost last video in the series, Astronomical Spectroscopy. How we know what we know. I'm Dewey Anderson. This is a 5-part series intended to explain how astronomers use spectroscopy to learn about stars, planets, galaxies, and the universe. The first video covered some background physics about light and heat that you need in order to understand spectroscopy. The second video discussed continuum radiation, or what's called the black body spectrum. We saw how it can be used to determine the temperature, luminosity, and ultimately the distance to stars. One of the things to remember from that video was the HR diagram. This shows a correlation between the temperature of a star and its intrinsic luminosity. The third video talked about spectral lines that come from discrete transitions and how they can be used to determine what stars are made of. This fourth video will discuss the Doppler effect, the shift in energy of photons due to the motion of the source. There's a bunch of different things we can learn from measuring that. Once again, I want to start with a quick reminder of some of the background physics stuff from part 1, just so that it's fresh in your mind. I talked about how we view light as a stream of light particles called photons. They have energy measured in electron volts, or EVs for short. Photons can be created when there are changes in electrically charged systems like electrons changing orbits in atoms. The rules of quantum mechanics say that only certain electron orbits are allowed in atoms. That means that when they change orbits, there's only a certain set of energy changes allowed. And that means that the photons that are emitted can only have energies from that discrete set. We say that those are discrete transitions. When that light is passed through a spectrometer, the photons are spread out based on energy, forming a set of lines at the energies for the emitted photons. This is what an image of the emission lines coming from hot hydrogen gas might look like. When we plot the spectrum as a graph, these spectral lines result in spikes in the graph if the electron is dropping down in energy, emitting a photon. We call these spectral emission lines. But it can also happen that photons of just the right energy knock electrons up to a higher orbit. Those photons don't make it to our detector. This results in dips in the graph of the spectrum. We call these spectral absorption lines. In actual practice, astronomers are usually measuring absorption lines. In the previous video, part 3, we saw how we could make a table of the energies possible for the different spectral lines. The great thing about this was that the set of energies was unique to each kind of atom. This means that if, say, I detect a photon being emitted or absorbed with an energy of 1.89 eV, I can see from the table that that's a hydrogen atom transition, and so I know that it came from hydrogen. This means that by looking at the set of spectral lines in the spectrum, it's possible to tell what the star is made of. A quick reminder, when I say 1.89 eV, I'm not including all the digits of precision that we really know. It's just easier to say. You'll see later that I'll include a few more digits when that difference matters. In this video, we're going to see that there's more information we can get by looking carefully at the plot of the spectral lines. We'll be looking into the Doppler effect, a shift in energy of photons due to the motion of the source. We'll see that this can tell us the speed of stars, and that can be used to detect binary stars and calculate the masses of stars. It could show early astronomers that Saturn's rings are not solid. By fitting absorption line profiles with a form that takes thermal Doppler broadening into account, we can distinguish absorption lines from interstellar gas clouds from the lines in the stars behind them. So that's how we can tell what those gas clouds are made of. There is an interesting spectral line that can be used to detect cold, thin hydrogen gas in the Milky Way, and we can use the motion of that gas to make a map of the Milky Way galaxy. The Doppler effect is also the basis for why astronomers have concluded that most of the matter in the universe is actually dark matter, stuff that doesn't shine, not the stuff we normally see. And the Doppler effect was also the first evidence of the Big Bang. So that's lots of stuff. Now, I've been talking about this as if you can always find the center of the absorption line right at the energy defined for that electronic transition. But it turns out the motion of the star can affect the position of that line. Now, this is the Doppler effect, and you're probably familiar with it from sound. Just as the pitch of a sound from a source moving toward you can be higher than if it were stationary, the energy of a photon is also higher if the source was moving toward you. It's kind of like someone throwing a ball at you from a moving truck. That ball can have a lot more energy than the person throwing it could provide. Now, that's pretty straightforward to picture when we're talking about photon emission. But we're talking about measuring absorption lines. Does that matter? Well, it turns out that the same thing happens with photon absorption. If the star is moving toward us, the photons that are 1.89 eV in the star's reference frame are absorbed by hydrogen atoms in the star's atmosphere. But from our point of view, that photon had a slightly higher energy. So the dark absorption line appears Doppler shifted to higher energy, just like an emission line would. So if a star is moving toward us, the absorption lines are all going to be shifted to higher energies. Gee, you might ask, doesn't that make it hard to identify which lines they are? Well, yes, it can, but we have the advantage that there's a whole bunch of absorption lines for each kind of atom, and they have a very distinctive spacing within the spectrum. If you slide all the lines of a hydrogen spectrum up in energy, it's still recognizable as the hydrogen spectrum. And that means you can identify the orbit number 2 to orbit number 3 transition and say, this was a 1.89 eV absorption line in the star's reference frame, but now it's been moved up to 1.9 eV due to its motion. And yes, there's a formula to tell you the velocity that provides that energy shift. So if we measure that 1.8892 EV absorption line, the one I've been calling 1.89, if we measure it at 1.8898 EV, we see that the star is coming toward us at almost 60 miles a second. The reverse happens if the star is moving away from us. The photon has less energy. Now picture someone on the back of a pickup truck throwing a ball at you as they speed away. Not a lot of energy in that ball. So an emission line from something moving away gets shifted to lower energy. And an absorption line from something moving away also gets shifted to lower energy. And the same formula still works. The energy difference will now be negative, so the velocity is negative, away from us. So if we measure that line at only 1.8886 eV, that means that it's going away at 59 miles a second. So the procedure is to identify the spectral lines from the spacing pattern, then measure how much the spectral energy has shifted up or down. Plug that into the Doppler shift formula to get the velocity. Now actually, this just tells us the speed toward or away from us, what's called the radial velocity. It doesn't tell us how much velocity it has going sideways. So that example star coming toward us might actually miss hitting us by a big margin, like maybe even light years. Now, by the way, there is a pair of somewhat inaccurate terms associated with Doppler shift that you will often hear. If you were looking at photons from the middle of the visual range, say yellow or green photons, then a Doppler shift toward higher energy would move those photons toward the blue part of the visual range. So astronomers would say that that light is blue shifted. And they have taken the habit of calling any photon shifted to higher energy as having been blue shifted. Even an ultraviolet photon being shifted to even higher energy is said to be blue shifted, even though that means that its energy has been shifted away from the blue part of the visible spectrum. Similarly, shifting yellow light toward lower energy moves it toward red, and is called red shifted. So any shift to lower energy is considered red shifted. Even when infrared light is shifted to lower energy away from the red part of the spectrum, it is still called red shifted. It's old terminology that reflects the fact that so much of early astronomy was done with visible light. And they are convenient terms, but just be aware that they don't always literally mean toward the blue or toward the red. They mean toward higher energy and toward lower energy. Now, one place these energy shifts come into play is when you're observing binary stars. That's when you have two stars orbiting each other. Now, they each actually orbit around the center of mass of the pair. That's located at the center of the two circles. If the plane of the orbit is such that we're seeing it near edge on, then each star will alternate between coming toward us and moving away from us. And the other star will be doing the opposite. So what you see in the spectrum is two sets of absorption lines very close together. The little vertical line here marks the energy for an unshifted photon. The one coming toward you is shifted to higher energy. The one moving away is shifted to lower energy. And as you watch them over the course of, say, a year or so, they'll actually move and trade places going back and forth. A lot of the stars in the sky are actually binary pairs. In fact, on the order of half the stars you see are binary pairs. Now, sometimes you can resolve the pair in a telescope, but sometimes they're too far away and too close together to be seen separately. But you can still see the absorption line split into pairs and move back and forth. That kind of binary star is called a spectroscopic binary because the proof that it's a binary comes from spectroscopy. And this information can actually be used to tell us the mass of the stars. The amount of the Doppler shift tells us how fast the stars are moving in their orbits. We can measure how long it takes for the spectral lines to go through a full back and forth cycle. That's their year. Knowing the speed and time, that tells us how far they traveled in one cycle. That tells us how big the orbits are, how far apart the stars are. Now remember, the reason the stars are orbiting each other is due to their mutual gravitational attraction. And the strength of that gravity affects how fast they move. And that strength is determined by how far apart they are and how massive each star is. But we just said we can determine how far apart they are. And that means we can figure out how massive they are. Now this can all be combined into two equations that let us solve for the two unknown masses. By the way, this spectral shift can also be used to detect the slight motion of a star due to the gravitational tug of a planet. Now you only see one absorption line, the one from the star, but it moves back and forth a tiny bit. You can't see a spectral line from the planet. But using the motion of one spectral line, you can still get what you need. This is one of the ways exoplanets are detected. And this is how we know planetary systems are pretty common. That's fine for binary pairs where the orbital plane is near edge on. But what about lone stars or binary pairs where the orbital plane is not near edge on? Well, it turns out that the physics suggests that there's a relationship between the mass of a star and its luminosity. It makes sense that there would be some kind of correlation. A more massive star will have a higher pressure in the core from all the weight of all that material above it. That means it'll also be hotter. The rate of fusion reactions that happen in the core depends on the pressure and temperature. More pressure, higher temperature means more fusion reactions. That means more energy generation. That means higher luminosity. Put it all together and you get more mass means higher luminosity. For stars that are on the main sequence in the HR diagram, the luminosity is proportional to a power of that mass. Now, it's a little more complicated than that, so the value of the exponent is actually a little different for different mass ranges. Binary stars, where we can calculate the mass, allow us to verify that physics. And that means that if we can tell the luminosity of a star, we can get a rough idea of its mass, even when it's out there on its own. Now, how did we get the luminosity? By measuring the spectrum to get the temperature and then using the HR diagram. Things we did in Part 2 and Part 3. So, here's how we know how massive stars are. A spectroscopic binary pair of stars will cause the spectral line to be split in two. Over time, the spectral lines move back and forth. That tells us by how much the radial speed is changing. The period of the spectral line motion tells us the period of the orbit of the stars. Knowing the speed and time tells us the size of the orbit. Physics equations can use all that to tell us the masses of the two stars. And based on the measurements with binary pairs, we can establish the rough mass-luminosity relationship so that we get a rough value for the mass of a lone star that is not part of a binary pair. There's another use for the Doppler effect that comes into play right here in our solar system. When Saturn's rings were first discovered, astronomers had no idea what they were. Were they a solid object? Long before Pioneer, Voyager, and Cassini missions, astronomers were able to use spectroscopy and the Doppler effect to show that the rings were not a solid object. They did this by measuring the Doppler shift of absorption lines in Saturn's rings. If the ring wasn't moving at all, there should be no Doppler shift. If the ring was spinning like a solid object, then the velocity at the outer edges of the ring would be faster than on the inner edge. If the ring was a bunch of tiny particles, all orbiting Saturn independently, then Kepler's laws of planetary motion say that the outer edge should be moving slower. These possibilities refer to the velocity curve that says how fast something should be moving based on the distance from the thing it's going around. This is what those three possibilities look like. You can see how the velocity under Kepler's laws decreases as you go out. The spinning disk increases linearly with distance. And naturally, if it ain't moving, the velocity is zero regardless of position. When they measured the Doppler shift of Saturn's rings, they found that it matched the Keplerian orbit velocity curve. Now here you see an image of Saturn, on the left, turned on its side. The spectrometer slit goes right down the middle of this image, crossing first one part of the ring at the top, then the planet itself, then the other side of the ring at the bottom. So at the top of the spectrum image, the right side of the picture, you see the spectrum of the part of the ring at the top. Then in the middle, you see the spectrum that spans the whole body of the planet, and then at the bottom, the spectrum of the other side of the ring. Look at any of those absorption lines. You can see that all the lines are tilted. Now, the position of a dark absorption line at the center of the planet would be the unshifted energy. So let me mark that on one particular line. At the bottom edge of the planet, the line is shifted to higher energy. That means it's coming toward us. At the top edge of the planet, you see that the line is shifted to lower energy. That means it's moving away from us. So you can actually see that Saturn is rotating just from the spectrum. And you can even measure the rotation speed of Saturn itself. But we're interested in the rings. If you look at the bottom band, which shows the spectrum of part of the ring, you can see two things. First, the spectral line is shifted to higher energy. So it's also moving toward us. Okay, so the ring rotates in the same direction as the planet. Good to know. But second, there is a slight tilt to the line that shows that the inner part of the ring is Doppler shifted more than the outer part of the ring. The inner part is moving toward us faster. The top band shows a similar thing. The line is shifted to lower energy, showing that that part of the ring is moving away from us, just like the planet. And the opposite tilt up there shows that the outer edge is receding from us slower than the inner edge. Parts of the ring closer to the planet are moving faster. That's Keplerian. Saturn's rings are individual particles. Not bad from several 100 million miles away. Staying within the solar system for a bit more, it turns out that the Doppler effect can also tell us information about the Sun, beyond the usual composition and temperature stuff. The Sun is a hot ball of plasma, a gas where a lot of the atoms have lost at least one electron. What we see as the surface of the Sun is actually just the place where the plasma gets dense enough that we can't see below it. This is called the photosphere. You can think of the Sun as a big blob floating in space, held together by its own gravity. Now imagine thumping the side of the floating blob. Because it's not a solid block, it will oscillate, somewhat similar to blobs of water you may have seen astronauts playing with in space. though there it's the surface tension of the water that provides the restoring force to the oscillation. With the sun, it's gravity. You can imagine that on a blob the size of the sun, a small localized thump would result in something very similar to a water wave moving out from where you thumped it. Both kinds of oscillations, an overall ringing like a bell or the spreading of a wave, cause the photosphere to move in and out, what would locally be up and down. This motion can actually be detected by the Doppler shift in spectral lines. So we can actually measure oscillations of the sun by using the Doppler effect. Now, the first such oscillation detected has a period of about 5 minutes, so it's called the 5-minute oscillation. It's basically the entire sun ringing at some natural resonant frequency, much like a giant spherical bell. The amplitude of the oscillation is only some tens of miles, so not much compared to the size of the sun. But 20 miles in 5 minutes is still fast enough that we can detect it in the spectrum. Now, the bells we humans make tend not to be spherical, but there is another spherical object whose oscillations scientists study: the Earth. In this case, the thumping comes from earthquakes, and the study of the oscillations is called seismology. The instruments they use to measure the oscillations are called seismometers. By putting seismometers in different places around the Earth, the scientists are able to detect differences in the speed of transmission of these oscillations, moving deep underground. Different transmission speeds indicate different material properties. And so, by measuring the oscillations at the surface of the Earth, scientists are able to determine structural properties deep within the Earth. Well, we might not have seismometers on the surface of the sun, but by measuring the Doppler shift at different locations on the sun's surface, we can still measure the oscillations. Solar flares and other disturbances play the role of earthquakes, thumping the sun to set off traveling waves. And from this, we can determine structural features inside the sun. We can determine the structure of sunspots below the surface. We can even detect sunspots when they are on the other side of the sun, facing away from us. We can see them coming before they rotate into view. This field of study is called helioseismology, and it's a fairly new discipline. Now, by the way, there's also a field called astroseismology that does the same kind of study of the atmospheres of stars. But it can't resolve different places in the photosphere, so it focuses on the overall oscillations of the star. In addition to measuring the velocities of stars and planets on the surface of the sun, spectroscopy is also used to study the interstellar medium, gas and dust clouds out in space. Now, often this is done by measuring the spectra of stars that lie behind the gas or dust cloud. And as the continuum starlight passes through the cloud, discrete photon energies are absorbed by the elements in the cloud. They can be distinguished from the absorption lines in the star spectrum by 2 ways. First, they often have a different Doppler shift from the absorption lines from the star. The star and the cloud have different velocities relative to Earth. But a second clue comes from the temperature. Gas clouds are very cold, whereas the atmosphere of stars are very hot. And this brings me to something I hinted at in the last video. Recall that spectral lines are not perfectly thin. The rules of quantum mechanics say that there is some natural width to the line. Even in an ideal situation, this line profile shows that even photons that don't have exactly the right energy still have a chance of getting absorbed. There is a messy equation that gives us the shape of this Lorentz profile. The general idea of the absorption line not being perfectly thin is called line broadening. One source of line broadening is quantum mechanics, and that is expressed in this formula. Another source of line broadening is called thermal Doppler broadening. Now, this comes about because of the individual motions of the atoms in the gas. Here I show a bunch of hydrogen atoms moving in different directions in a gas. Some have their electrons in orbit number 2, some in orbit 1. Only a few of the atoms are shown motionless. With respect to any detector, each atom will have its own Doppler shift. That means that the energy of the photons it emits or absorbs will be shifted in the spectrum plot. This is just like what I showed at the beginning when talking about the shift of spectral lines in a star. But now we have a bunch of essentially random shifts applied to each of the photons coming from or through the gas. Some will shift higher, some will shift lower. All of this will tend to smear out the shape of the Lorentz profile. And the hotter the gas gets, the larger the range of relative velocities. So a hotter gas will tend to smear out the Lorentz profile more. So if we have an absorption line, say from the spectrum of the sun, it might look like this. But if the sun's atmosphere was hotter, that absorption line would be spread out a little. Notice that it's also not quite as deep. Whereas if the sun's atmosphere was cooler, that absorption line would be thinner and deeper. So in taking spectroscopic measurements of light from a star passing through a cold interstellar gas cloud, absorption lines from the gas will be deep and narrow, one might say crisp, whereas the absorption lines from the star's atmosphere will be much broader. The combination of the ideal Lorentz profile and the thermal Doppler broadening is called the Voigt profile. And of course, there are messy equations for working that out. So instead of fitting a measured spectrum to the Lorentz profile, it's actually fit to a Voigt profile. And, oh look, that's another direct measurement of the temperature. In addition to measuring the absorption lines, gas and dust clouds in star-forming regions are often studied by their emission spectra. Stars that have already formed will illuminate the cloud and cause some electrons to get knocked up in level. For the part of the cloud along the same line of sight as the star, that's just the process of making absorption lines. But for parts of the cloud that are not on that line of sight, we actually see the emitted photons as the electrons fall back down. They send out photons in all directions, and some of those photons come our way. So we see the cloud as emission lines. In addition to these fairly dense clouds, there's also a lot of hydrogen gas pervading the entire Milky Way. And as it happens, cold hydrogen gas sitting out in space will actually emit some very low-energy photons, and we can use that to map the Milky Way. Now, I talked about the ground state in hydrogen atoms. Well, it turns out that if you look really carefully, that ground state is actually split in two. It's not two different orbit heights. It's the fact that the electron itself is spinning, like the Earth spinning on its axis as it goes around the sun. And if it's spinning in the same direction as the orbital motion, then that's a slightly higher energy than if it's spinning in the opposite direction. The energy difference between these two states is very small, 6/100,000ths of an eV. Hardly noticeable if an electron is dropping down from orbit 2. But if left to itself, over a period of about 700,000 years on average, the electron on the left will flip over to the lower energy state, sending off a 0.00006 eV photon in the process. If we go back to the drawing of the photon energy spectrum, you see that this energy, about 10 to the minus 5, is actually in the radio wave region, so it can be detected by radio telescopes as an emission line. Now, while it's very rare for a hydrogen atom to do this, there's a lot of hydrogen out there in the galaxy, and so it can be detected. As part of the swirling mass of stars and gas that's going around the center of the Milky Way, this gas has a velocity relative to us. And by measuring the Doppler shift of this low-energy emission line, astronomers can figure out where in the spinning disk it is. And the strength of the line will indicate how much hydrogen is there. And so we can map out the density of the hydrogen gas in the Milky Way. This is what that map looks like. Now, there's some places where we can't figure out the position because there isn't enough radial motion toward or away from us. And that's why you see those blank wedges. The tips of those wedges are where the sun is. But the presence of multiple spiral arms, just like we see in other spiral galaxies, is pretty clear. Not bad, given how hard it is to see the layout of the forest when you're surrounded by trees. Working our way farther out into space, we can measure the velocity curves of other spinning galaxies. This is kind of like the measurement of Saturn's rings. Now, most of the visible matter is in the core and inner part of the galaxy, but since that's not just a central point, the velocity curve actually starts at zero, rises up as you move outward, and then once you're out past most of the mass, it's expected to descend, like the Keplerian curve I showed before. That's the dashed curve. But when astronomers measure the speed of stars moving outside of that, they find that it doesn't fit the Keplerian curve. Even farther out, where it's hard to find stars, the motion of the hydrogen gas, observations in blue, can be measured from the spin flip I talked about. The actual observed velocity curve doesn't drop down with distance. For this to be the case, there must be more mass farther out than we can see. This implies that there is some kind of matter out there that doesn't shine. Dark matter. We can even go out to a larger scale by looking at clusters of galaxies. There, we can use the Doppler effect to measure the speeds of the galaxies within the cluster. And it turns out those galaxies are moving so fast that it wouldn't take long for them to no longer be a cluster. So they must be gravitationally bound together. And knowing the speeds, kind of like that binary star calculation, it's possible to get a rough value for the mass of the entire cluster. It has to be enough mass to keep galaxies moving that fast from flying away from the cluster. But it turns out that if you add up the visible mass, the rough mass estimates of the visible galaxies, you don't get enough mass. Not nearly enough. And this is more evidence of there being dark matter in the universe. Something we can't see has to be keeping those galaxies from flying apart. It's now believed that there is something like 5 times as much dark matter out there as there is luminous matter. Most of the universe is made of stuff we can't see. And we've really no idea what it is. Guesses range from exotic subatomic elementary particles, some called weakly interacting massive particles, with the clever acronym WIMP, or WIMP, to lots and lots of small planet-like objects in the galactic halo, a roughly spherical region around galaxies. Some of these are called massive compact halo objects, with the equally clever acronym MACHO, or machos. So it comes down to whether dark matter is wimpy or macho. And as long as I'm expanding the size scale here, I might as well go all the way. Edwin Hubble used the Doppler shift of galaxies to determine that, except for the closest galaxies right here, all galaxies are moving away from us. Now this is a plot showing the distance to a galaxy on the x-axis and the recession speed of the galaxy, how fast it's moving away from us, on the y-axis. And you can see that the farther away from us they are, the faster they're going. Conclusion: the universe is expanding. The entire universe is expanding. Run the clock backwards, and you find that everything, that's everything in the universe, was all crammed together in one place about 14 billion years ago. Run the clock forward from there, and you get the Big Bang Theory. This shows you the original plot Hubble did on the left, with red lines marking how much you have to zoom in to see that on the bigger plot on the right. You can see how astronomers have been able to extend that to much farther distances and get a very convincing fit to the line. Because they're all moving away, the Doppler shift is always to lower energy photons. Recall that the general term for this is redshift. The overall Doppler shift of all distant galaxies is called the cosmological redshift. In an interesting flip, we now use that in the other direction, and by measuring the amount of Doppler shift, we use that to determine the distance to far-off galaxies. So let's recap this Doppler shift business. The motion of a source towards a detector shifts the photons to higher energy. Astronomers call this blue shift. The motion of a source away from a detector shifts the photons to lower energy. Astronomers call this red shift. There is an equation so that we can convert the energy shift into a radial velocity. We can use this to determine how fast stars are moving, radially at least, toward or away from us. We can detect spectroscopic binary stars and get their orbital period, orbital size, and the mass of the stars. The Keplerian velocity curve for Saturn's rings showed they're made of small particles orbiting Saturn, not a solid disk. The Voigt profile, that combination of the ideal Lorentz profile for the shape of an absorption line and the Doppler broadening due to thermal motions of the atoms in a gas, can be used to determine the temperature of interstellar gas clouds and distinguish the thin absorption lines in the cold gas from those in the hot star behind the gas. The velocity of cold hydrogen in the Milky Way allows us to construct a map of the galaxy. That's like mapping a forest from inside when you're surrounded by trees. The non-Keplerian velocity curves for galaxies implies the presence of dark matter, stuff that isn't shining. And galaxies in clusters are moving too fast if the only mass in the cluster is the luminous matter that we see. There must be dark matter. In fact, most gravitating matter is dark matter, stuff we can't see. Oh, and Hubble discovered the expansion of the universe. That's a lot of stuff, all coming from just being able to measure the energy shift of photons. Okay, 4 down, 1 video to go. The next one is a short one about the Zeeman effect, which can be used to detect and measure magnetic fields. See you there.